I know I started. I gave the message, but start by 10:20. Okay, now it is 10:20. Let us start. Is Pranav Menon here? You can make use of the group chat window here. Pranav.
So I'm present, sir.
Okay. Akhil Kumar, is it Ahalya? Is Akhil Kumar standing for Ahalya's name here? Suprativ Rai? Is Suprativ Rai here? Oh, that's fine. Shivani is also here. Vamsi Krishna here. Who is this Mike Robinson? What is the actual name of Mike Robinson? Om Saha. Okay. Okay. Sharun Iyer. Sharun Iyer absent here. Sharun Iyer left group chat. Okay. It's all right. Probably some people may be making use of YouTube, but there is one disadvantage with that, even though there is one advantage. You can't go for reciprocating. Okay, it's all right. Nawaz Asif Sheikh is also there now? Okay, that's right. So we'll go for one thing. Suprativ Rai, try to tell me one thing here. What is the first law of Kirchhoff? You can just, raise the voice of your microphone, you can start speaking.
Sir, the algebraic sum of electric current at a junction is the law of
No, why you are speaking in quite a, dull manner? Be active in person.
Sir, the first law says if it is the algebraic sum of electric current at a junction is zero all the time.
Algebraic sum of currents meeting at junction is zero.
Junction is zero.
All right, what is its other name?
Sir, it can be called as junction law, or it can be called as Kirchhoff current laws.
It is Kirchhoff's current law, it is junction theorem, or it is law of conservation. Okay.
Yes, sir. Yes, sir.
All right, you can just lower your microphone. Then Shivani, what is second law of Kirchhoff? If possible, you raise the voice of your microphone and speak, and then you can lower. Second law of Kirchhoff. Are you turning the pages, Shivani? You must be thorough, my dear. All right, what about Ahalya Kumar? Ahalya Kumar. Okay. Any one of you take the chance?
The algebraic sum of potential differences and EMFs in a closed loop is zero.
Zero. Okay. Is it Nawaz Asif Sheikh speaking?
No, sir, Soumya Chaudhary.
Oh, Saumya, that's good. Then, gentlemen, why can't you tell me the sign convention that we use in second law? What is the sign?
Sir, potential drops are taken as negative and potential raises are taken as positive.
That's good. Then, okay. Potential in a closed loop is drop, negative, raise, positive. That's fine. Okay. PDs and EMF. Shivani, why can't you give me answer for one more thing? What is the sign convention that we have used during first law? You can immediately type the answer or you can speak if your microphone is working. What is the sign convention used? Towards positive, but you have to say, towards junction. Currents towards the junction are taken as positive. Currents away from the junction are taken as negative. Is it not, Vamsi Krishna? All right. Anyhow, that's okay. I was talking to you something about Wheatstone's bridge. Why can't you start talking about that Wheatstone's bridge? Shreya Sundararaman here. Shreya Sundararaman left group. All right. Pranshul Thakur.
Yes, sir.
Why you are late, my dear?
Sir, actually, I was trying, sir. It was not coming, sir.
All right. Ragini also entered the picture just now. Okay. Ragini, can you go for describing Wheatstone's bridge in your own words? What is Wheatstone's bridge?
Sir, it is just the similar picture as we took in the balanced bridge. It is like the four arms are connected together.
Okay. The minute you look at the picture, how the shape looks like?
Like a square.
Right. With how many arms?
4 arms.
Okay. What is contained in these 4 arms?
Each arm consists of one resistance.
Okay.
And generally we either take the diagonal with the galvanometer.
Okay, no, across one diagonal what is connected, across other what is connected?
Across one diagonal, galvanometer is connected.
Okay, what is the other diagonal connection?
With one cell and one key.
Plug key.
Yeah.
Okay. Now we go for speaking to Pranshul. No, whenever necessary, please raise your microphone and speak and lower that one so that it will not give problem. Pranshul?
Yes, sir.
You tell me, what exactly you mean by balancing condition of a Wheatstone's bridge?
Sir, balancing condition means the resistors are arranged in such a way that the current through the galvanometer is zero. Sir.
Okay, when that occurs?
Sir, when R1 by R2 equal to R3 by R4, with the ratio is same, sir.
No, my dear, R1, R2, that's okay. By adjusting the resistances, you are seeing that the potential difference across the one diagonal becomes zero.
Yes, sir.
Is it not? So as and when you do that, of course, as you are telling, of course, R1 by R2, R3, P by Q, R by S, it is all. Only when diagram is in front of you, clearly you can interpret. Okay, then I want to ask you one more thing. What can you say about the balancing condition by interchanging galvanometer and power source?
Sir, the condition will remain the same, sir.
Remain the same. Okay. Then Nawaz Asif Sheikh will tell us one thing. What is the advantage of Wheatstone's bridge? What is the advantage? The value of unknown resistance can be found. Is it the only advantage, my dear? No, no. Both things are same. Okay, we can find the unknown resistance. No, what are the other advantages? It used to determine what? My dear, Vamsi Krishna is also saying same thing repeated by 3 people. I am looking for some other advantages.
Some series and parallel resistance formula can be verified with that.
That is true. One more.
And using the formula R is equal to rho L by A, resistivity of the wire can be calculated.
That's what. Resistivity of a material can be, even Pranshul is saying the same occurs. That way it can be determined. Okay. Altogether these are the specific resistance. Vamsi Krishna, it is nothing but resistivity only, no? Okay. Then, anyhow, let us go for... Okay. Let us go for looking at one more situation here. Just, if your condition is permitting, be ready with your notebooks so that you can do one more thing. I want to tell you something else. It is, this one. No, 1 minute. It is writing in a very quiet, thin way. I want to make it thick. Okay. Let us go for looking at this. That is...
Sir, I can't see the screen, sir.
You are not able to see the screen?
Yes,
is
sir.
it the case with...
Yes, sir.
Oh, 1 minute. Don't worry, my dear. Thank you. You said that you are not able to see, na? We'll make you see. Sure. Are you seeing now?
Yes.
No?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Sir.
Okay. If all of you are seeing, hello? Then, this is this one, It is meter bridge. It is meter bridge. Okay, what is this? Let me talk to you in one way. I am drawing a diagram where we are showing 2 metal plates, thick metal plates, bent in the form of letter L. This is one plate. This is, of course, the straight plate in between. There is one more plate here. This is also bent in the form of letter L. Now, for making electrical connections, we will be having small screws, and we call them as binding terminals. These round things indicate screws, which I make them little bit loose. I introduce some wire in between, I'll make it tight. These are known as binding terminals. They are meant for binding the wire. Okay. Now, for convenience, let me call this gap between the plates as left gap. This is left gap. And of course, this is the right gap. It is right. These two are 2 gaps. In one gap, let me introduce one wire of unknown resistance. Let me call it as X. Unknown, algebra style, X. In the right gap, I will introduce a known resistance. But here, for a while, I should disassociate from this topic. I am talking about a resistance box. Probably some of you in physics lab, you might have seen it. It is simply a piece of wire. A piece of wire made up of a different material and different length. And if at all you come across one such box in the physics laboratory where different resistances are possible, people call this as resistance box. Resistance box, it helps you in keeping 1 ohm, 2 ohm, 12 ohm, 13 ohm, anything of your choice you can maintain. Let me say that such unknown that known resistance box. Actually, it is a resistance box whose resistance value we know confidently, and you are going to handle such things in the physics lab. I'll show you later. This is known resistance R, this is unknown resistance X. They are used to fill up the left and right gaps. Now, please see one more thing, my dear. Starting from this bottom, I want to go for showing you one straight wire. Okay, it is straight wire. I take the help of this. Okay, one straight wire I'm showing here, and you know, 1 minute. One small diagram management will make here. My idea is to show this as a straight wire. It's not the question of my drawing straight, but I should actually show you. And this wire is made up of one special material. Please remember, its name is manganine. Manganine. It is an alloy of some materials like manganese, aluminium, iron. We call it as manganine. What is its speciality? It was found that some materials will show fluctuations with resistance in temperature. For 2 minutes, let me just, keep this topic aside. I want to tell you something else. We'll come back to this meter bridge. Let this diagram stay by our side. In between, let me tell you one thing. When you go for taking one metal wire, at room temperature, its resistance is something. When you go for heating it, no doubt, physically whenever one wire is heated, according to our thermal expansion of solids studied in 11th class, the length is likely to slightly increase. The cross-sectional area is also slightly going to increase. But from the current electricity point of view, we say that resistance is offered by a metal due to the lattice vibrations inside. Every material is having some atoms. The combination of atoms we call as a lattice. Depending on the heat energy, they will be vibrating. Depending on their degree of vibration, electrons traveling in them will experience different difficulties. Compared to room temperature, if somebody goes for heating the metal, if they go for taking it to a higher temperature, the lattice vibrational frequency was found to be more. Whenever lattice vibration frequency becomes more, electrons face great difficulty in traveling. Then people say, sir, metal wire resistance increased. So metal wire resistance increases as the temperature of the wire increases. Then there is one arbitrary formula for this. Better if you remember one thing. Let us say that at 0 degrees centigrade, the resistance of a wire is R0. And at T degrees centigrade, let the resistance of the wire be RT. After all, I am measuring the temperatures in degrees centigrade or Celsius. These are the corresponding resistances of the metallic wire. Then people say that RT and R0 are related by this formula. There is nothing like derivation for this, my dear, but you are supposed to remember RT is equal to R0 into 1 plus alpha T. Then if you don't mind, bracket, and I will write like R0 plus R0 alpha T, or R0 alpha T is nothing but RT minus R0. This alpha, the term which we have introduced here, is given one special name. Its name is temperature coefficient of resistance. I am writing here, it is temperature coefficient of resistance. That is the name given to alpha. Then what is that alpha equal to? It is RT minus R0 divided by R0 into T. After all, we started with this ready-made formula. we are coming to this conclusion. The name given to alpha is temperature coefficient of resistance. Then, if you don't mind, I have taken two temperatures 0 degree centigrade, T degree centigrade. But there is no rule such. You can take two temperatures, some T1, T2. Let us say that at T1 degree centigrade temperature, the electrical resistance of a wire is R1. And that at T2 degree centigrade temperature, the electrical resistance is R2. Means we are talking about two resistances, two corresponding temperatures in centigrade scale. They are related in this manner, my dear. Alpha is equal to R2 minus R1 by, after all, R1 T2 minus R2 T1. R2 T1. You know, in one way, I can go for saying like this. I don't know. You must be remembering one thing. Do you remember coefficient of linear expansion that you have written in case of solids? Thermal expansion. Alpha is equal to L2 minus L1 by, do you remember? Nothing is coming to your brain? Nothing? In 11th class, what you have written, my dear? Temperature coefficient of, coefficient of linear expansion of a solid by L1 into T2 minus T1, no? So better, I advise you to remember one thing. Exactly in the same style, we'll go for writing. Hello? There is some disturbance here. No, one may have to go for muting the microphone, please. Okay, then do that, there won't be much problem. Alpha is equal to, comparing with the above formula, shall I write like this? R2 minus R1 by R1 into T2 minus T1. It is no big new formula for you. Instead of L, I am writing R. This is temperature coefficient of resistance formula. So, what will be the SI unit for this? It is per Kelvin or Kelvin inverse. This is same. To be frank, this formula same. But here our attention is on T degree, 0 degree centigrade. Here any two different temperatures and any two corresponding to resistances. This is temperature coefficient of resistance. But here, let me talk to you about one more thing. This temperature coefficient of resistance alpha value is different for different metals, but one thing is common. For all metals, it is positive. What does it mean, my dear? As temperature increases, resistance also increases when alpha is positive. Now, if you think in the reverse manner, for a metal wire, if you go on decreasing the temperature, as you make it cool, at one temperature, the resistance should become equal to 0. Exactly, whenever the resistance of a metal becomes very small, it becomes almost to 0. At that particular temperature, people say that the wire is behaving like a superconductor. I am using a new word. Please, my dear, catch this point. Superconductor is a material whose conductivity is very large or whose resistivity is almost 0. But that superconductor story arises only when the temperature coefficient of resistance becomes very small. That occurs at very low temperatures. As theory says, the alpha value of any material becomes 0 at absolute 0. Absolute 0 is minus 273.15 degrees centigrade, no? That is known as absolute 0, 0K. So at 0K, all metals will become superconductors, but some metals were found to be becoming superconductors even at a bit lower temperatures, need not be 0K, even if you take them to some minus 40 to minus 50 degrees centigrade. They are of course superconductors. We have some special information about it. We'll come to it later. But just to remember one thing, because I don't want to keep you in dark about this and to go with meter bits. My intention is to say that alpha value is positive for metals. In general, it means that resistance increases for metals as temperature increases, or the converse is also correct. If you decrease the resistance, if you decrease the temperature, resistance also decreases. Now, there are some materials like superconductors. You must be knowing them as titanium and silicon. These superconductor materials used in semiconductor electronics are having their alpha value negative for semiconductor materials. What is the meaning of that? As the temperature increases, resistance decreases. When you say as temperature increases, resistance decreases, definitely a condition will come where to go on heating one material, semiconductor, at high temperature, it should become a very good conductor, superconductor. So, for semiconductors, metals, there is something. But remember, for some materials, this value of alpha was found to be almost zero. What is of that, sir? When you say alpha is almost zero, indirectly you are saying that whether you heat that material, whether you cool that material, resistance is not going to change drastically. And after all, such materials are used for preparing resistance boxes, because while making use of resistance box, we use metals. Probably one metal wire used in your resistance box may be having 10 ohms resistance today in summer. Even in winter or in rainy season, always its value should remain the same 10 ohms. That is possible only when you make use of a material with the smallest value of alpha. After all, at that stage, our hero metal manganese enters the picture. Remember, manganese is a material, it is an alloy whose alpha value is almost zero, which means that it is wonderfully useful to prepare resistance boxes in the physics laboratory. Now, when we are talking about the present topic, meter bridge, we are taking the help of such a manganese wire. And now, we will go back to our lesson. Remember only one small thing. Electrical resistance is affected by temperature. That electrical resistance temperature dependence is given by one mathematical formula. In that formula, alpha is temperature coefficient of resistance. If you prefer a material with alpha value almost zero or very, very low, whether you take it at whether you use it at high temperature or low temperature, in whatever season you want, the resistance will be almost the same. Such qualification is there for manganese material. So manganese material with uniform thickness and some fixed length of about 1 meter is preferred for our present meter bridge experiment. This is one flashback for our part. Then anyhow, let me come back to one thing. Again, I'll make our meter bridge a prime thing. 1 minute. All this you would have noted, or it is enough if you understand. I'll go back to our actual thing, that is nothing but this. Okay, now our meter bridge is again coming to limelight. We are bringing that back to the main platform. Okay, right. It is sitting here. Let us go for using this one. I told you, thick metal plates in the form of letter L are used 2 in number. In between there is another thick metal plate. There are 2 gaps, left gap, right gap. In the left gap, let us use one unknown resistance. In the right gap, let us use one known resistance R, and let us go for connecting these 2 points. After all, let me go for calling this point as A, this point as some B, and in between we connected one uniform wire made up of manganese. You know behind the curtain story. Why manganese means there is again other story. Okay, then I want to tell you something else. Let me go for doing something here. Starting from this terminal, I will go for using one cell, positive, negative. We go for connecting one plug key by the side of it only to control the current to stop or start. It is something like a switch. Then I am taking the help of one resistor. But remember, over the resistor, if I show one arrow like this, and if I continue like this, I believe you must be knowing it is given the name rheostat. Rheostat is the other name for variable resistor. By moving one jockey, the length of the wire coming into contact can be changed, which means that resistance can be made more or less according to our convenience. Remember, the popular symbol for variable resistance is, you can draw one resistor diagram. Over that, even if you put one arrow, it is the circuit symbol for this one only, rheostat. This is variable resistance or rheostat RH. This is the plug key. This is the source of EMF. This much circuit I have drawn. And one more thing, there is some point here, midpoint. Let me go for calling this as some C, because already I use alphabets A and B. This is C. That middle terminal, I told you, these are the binding terminals, connecting terminals. That C is connected to one sensitive galvanometer. Yesterday I was telling you, a galvanometer is represented with a circle and an arrow inside symbol. That galvanometer is connected to one rectangular box. Let me go for calling that rectangular box as HR, high resistance. It is again connected to one ball pen like thing which can be attached to a wire. To simply think this as a wire, a long wire connected to a ball pen like thing, people call this as jockey. Its name is jockey. It is something appearing like a ball pen. After all, in case of a ball pen, I want to show you this much. If this is the outer plastic cap, inside you see a refill. But in case of jockey, you see the inside one metallic wire. After all, this end of the wire, people call it as symbolically jockey. A nut and nut screw arrangement. You can involve one wire. When you enter the physics lab or bringing them into the class, later I will show you. But anyhow, the jockey is connected. After all, people go for calling this a circuit diagram. I am sure all of you might have drawn this circuit diagram in your notebooks. Okay. Then let me go for calling this as the jockey J. Let us see the experiment. Once if you make up these connections, in the physics lab, it is one technique to connect all the unknown things, keeping one circuit arrangement in front of us. It's not difficult. Let us go for connecting everything in this style. Then people say, the meter bridge is ready. But I told you, please remember, here there is a wire which is 1 meter long. This is 1 meter long wire AB made up of manganese. Since we are going to use the principle of Wheatstone's bridge here, since we are taking the length of 1 meter wire here, combining these two, people started calling this as meter bridge. I am sure you must be knowing one thing, sir. Meter spelling is M-E-T-R-E correct or M-E-T-E-R correct? Both words are meter only. But if you are using watt meter, voltmeter, ammeter, use the spelling M-E-T-E-R. Small observation. If you are talking about 1 meter, 2 meter for measurement purpose, use M-E-T-R-E. Now, after all, my interest is to talk about 1 meter long length of a wire making use of Wheatstone's bridge arrangement. So I am justified in calling this as meter, M-E-T-R-E meter bridge. Okay. Now let us go for looking at this situation. What is actually this experiment? Everything you'll understand. Be slow. After making all the connections I told you, this jockey is something that you can lift like a ball pen easily. You can lift, you can put it anywhere. that type of putting anywhere on this wire AB is given one technical name. We say that we are probing. P-R-O-B-I-G, probing. Now, in the name of probing, we start putting this jockey first at A. Immediately, you know, in galvanometer, if this is the galvanometer round part, if this is the circular scale, the galvanometer pointer will go to left side. When this happens, my dear, when you keep the jockey at A, when you keep the jockey at B, the same pointer will go to the other right end. To this end it will go. Then we certify that, sir, we made connections right. Our connections are said to be right. Remember, happily, if you are feeling, you write something on your own. Do it. It is something like a Chandamama story. No problem at all. You are keeping the jockey first at A. You are seeing left deflection. When galvanometer pointer is moving, observe. I am using one technical word, deflection. The pointer deflects towards left. When jockey is kept at B, it gets deflected towards right. Then only I am sure that my connections are correct. If they are not correct, how to do? That is our physics practical. Then once again, I will come to your lab, I will talk to you about it. Then, what is the actual experiment? You know, I go on moving the jockey starting from A, gradually, it's not just moving, lifting the jockey and keeping it at different points separated by millimeter like that. If you go on doing, say by the time your jockey has come up to this point J, let us say that galvanometer deflection has become 0. With our previous knowledge, if you don't mind, I say then galvanometer current is 0, deflection becomes 0 only then. So Ig is equal to 0 condition appeared. Then people say meter bridge is balanced. When meter bridge is balanced, the length between A and B, let me call it as L centimeter. My dear, when this is L centimeter, when total wire is exactly 100 centimeter, why can't I say that the JB length of the wire is nothing but 100 minus L centimeter? Is it okay? 100 minus L centimeter is JB, whereas L centimeters is nothing but AJ, and people go for calling that L with a special pet name. It is given the name balancing length of meter bridge. It is balancing length. And one more doubt, sir, which one I have to call as balancing length? Print one idea in your brain. After all, that L is just below X, where X is unknown resistance. So whatever is coming opposite to X you call as balancing length. Obviously the remaining will be 100 minus L. Is it okay? Then at this stage I want to tell you something else. No, just you try to follow. I am that sure with least difficulty happily you can. No, I am making one small management with the diagram. We are keeping this diagram here because this is not a big board. I can't do the remaining management. So I am slowly shifting this diagram to this place. Okay, now I have enough gap here to meddle with. Then people go for calling this a circuit diagram, whatever is appearing now on the screen. Looking at that, we will draw another diagram. It is not actually the actual diagram, but people call it as equivalent diagram. You can also take that side heading. This is equivalent diagram. This is what I am going to draw now. Equivalent diagram. You know, for drawing this, please see what I am doing. This point C, of course, you think that you are pulling that point J down, then the picture appears like this. Please see what I am doing here. I pulled that point J, just I am imagining like that. Then that point J I will show down. Naturally the point C will be up. The point A will come to left side. Point B will come to right side. My dear, are you able to follow? I am simply thinking you to imagine the same circuit diagram in this style. Take A and B to left and right extremes. Let C go up. Let J come down. Then, looking at the diagram, you tell me how much resistance is there between A and C, my dears? It is X. Between A and C, please look at the diagram. You may say, sir, some thick metal plate is there. Don't worry. R is equal to rho L by A. In this formula, if cross-sectional area is very large, resistance will be almost equal to 0. That is why we have taken thick metal plate. So thick metal plate resistance is 0. That is why you are not considering it. Simply you are thinking that between A and C in the diagram, only one resistance is there. Please see, I am calling this as X. Between C and B, how much is there, sir, again? It is known resistance R. I am putting there, of course, the same symbol. I am going for calling this as known resistance R. Then, how much is there between A and J? Here, one thinking. You have taken manganese wire. Because that manganese wire is having uniform cross-sectional area and it is made up of one fixed material with some resistivity, you are justified in saying that every 1 centimeter length of manganese wire, let it have rho ohm resistance. Something, my dear, some symbol I am using. For 1 centimeter, let us say resistance is rho ohm. Because balancing length is L centimeter length will be having how much resistance? L rho. Because you know resistance and length are directly proportional. L rho ohm. Similarly, in JB, of course, don't forget this L centimeter is appearing between A and J. Like that, between J and B, how much is appearing? 100 minus L centimeter. 100 minus L centimeter will be having how much resistance? 100 minus L into rho ohm. For L centimeter, L rho. 100 minus L centimeter, 100 minus L into rho ohm resistance. Now, let me incorporate these values in this equivalent diagram. Please see what I am doing. Between A and J, I will write L rho. Between J and B, how much is there, sir? Between J and B, I am writing 100 minus L into rho. Look at one important point. We have to answer few questions. Sir, why you are involving high resistance? You know, when you are trying to balance the bridge, you are allowing different currents through galvanometer. Galvanometer is always a sensitive instrument. It can bear a maximum current of few milliamperes. Don't worry, I will repeat this later, but just remember one thing. Every galvanometer is having one maximum value of current which it can bear. That's all. Its bearable limit. Saturation current is that. People call it a saturation current. And if at all the current exceeds beyond that, the galvanometer coil will burn off. It gets heated up, it will burn off. Simply in the physics lab, you see some smoke coming out of the galvanometer. If you want to avoid that headache, you must allow low current. Even accidentally, if high current comes, if you use high resistance, naturally, you know, low current flows. Galvanometer gets protected. So remember, high resistance. This high resistance value, popularly known as meg ohm. Meg ohm is nothing but mega, giga, tera, peta, exa. You heard in 11th class. Meg ohm is 10 to the power of 6 ohm. That high resistance is used to protect galvanometer coil burning due to high currents if at all accidentally they enter. But anyhow, even if that high resistance is not there, in the balancing condition because current is 0, happily our galvanometer will work. Please see, between C and J, I am showing galvanometer. My dear, actual circuit diagram is this. But when you draw it in this equivalent diagram style, are you not seeing? Of course, between A and J only, there is one cell, plug key, rheostat, whatever it is. But anyhow, is not this diagram appearing like our Wheatstone's bridge? That is why people say that meter bridge works with the principle of Wheatstone's bridge. Then what is the condition, balancing condition for Wheatstone's bridge? We studied P by Q is equal to R by S. But now, in the name of P, there is X. In the name of Q, there is R. In the name of these two, we have L rho and 100 minus L into rho. If you write like this rho gets cancelled. From this, why can't you tell me the formula for X? X is equal to cross multiply R L by 100 minus L. Using this formula, you can find the unknown wire resistance X. This is the beauty of this meter bridge. Meter bridge makes use of Wheatstone's bridge principle only, but people will say that, sir, meter bridge is very, very sensitive compared to Wheatstone's bridge. Why? Anybody? Meter bridge, which we have studied now, of course, from the board exam point of view, it is an essay question. Are you able to understand the actual circuit diagram and meanings of all the terms? Then the equivalent diagram we are drawing here. Then the minute you write it, balancing condition will appear. You can go for concluding with this formula, X is equal to RL by 100 minus L. Then, in what way this meter bridge is sensitive, sir? Anybody? Why people say that? Sir, accurately you can measure the wire resistance using meter bridge. Because in case of Wheatstone's bridge, for the sake of theory, we were saying about P, Q, R, S. These are the different resistances. But if you are using one wire, on the wire I told you about probing, where you move the jockey from one point to another point by lifting. Maybe if you are quite sensitive, you move it by 1 millimeter or half millimeter. So you can have all possible values. I should tell you one thing here. If you are in your house, if you are making use of a regulator for your ceiling fan, there are two types of regulators. By this time you might have seen, few regulators will be having 1, 2, 3, 4, maybe 5 numbers. When you go for rotating the knob of your fan regulator, your fan starts running with some low speed for 1. Means your resistance involved is very high. Keep your hand on that resistance box, fan regulator, it appears hot because current is flowing through a resistor. Definitely some amount of electric energy gets converted into heat energy, it appears hot. Then you better do like this. You slightly go for rotating it to 2, then your fan starts running a bit more speedily, which means that you lower the resistance. After all, the regulator is nothing but you choosing different resistances, maybe 20 ohms, 40 ohm, 60 ohm, 80 ohm, that way you are increasing or decreasing. But nowadays in the market, maybe from the last 7 to 8 years, you are seeing electronic regulators where you will get either no resistance in the circuit or the whole resistance, anything in between. Happily you can rotate them freely, not with a click sound, ordinarily 1, 2, 3, no. In some regulators you can happily rotate gradually from one to the other. Such regulators can be used to get any resistance between a 0 and maximum. Actually, such resistances nowadays in the gift shops, they are using for dip and dim. You can go for making the light dim, dip, just by rotating the knob. That is variable resistor. Anyhow, here we are using a jockey. We are able to move the jockey by every 1 millimeter. By doing that, you are able to change the resistance with all care. Exceptionally wonderful value. Using resistance box, I may get 50 ohm, 60 ohm, but I cannot get 51.57 ohm. But such a small thing is also possible in case of our meter bridge. That is why tomorrow, when you are performing physics experiment with meter bridge, your balancing length may be 31.5 centimeter, right? Maybe 27.2 centimeter. Don't think that you are wrong. No, it can be a fraction also that way. So remember, definitely this is very sensitive. Now, let me conclude saying one more thing. Our meter bridge arrangement has all the advantages of Wheatson's bridge. The minute I say that, in your mind something must be coming clearly. I can go for verifying series and parallel grouping of resistances. I can find unknown resistance of the wire, and by using the Tx, please look at the diagram. After all, this X is nothing but unknown resistance. It is a wire. If I go for using one wire material, if I know its length and cross-sectional area, of course we do that also in physics lab, cross-sectional area with screw gauge, we will find
How will sir join Ray? It's already full now. Pranay should move.
If you keep quiet, sir will join, dude.